Alright, so with this video we're going to take a look at implicit differentiation and what that is compared to taking derivatives like we used to. Differentiation is of course just a fancy way of saying derivative. So why do we use this? First we want to talk about why we're using it and where we're going with it. So I want you to imagine a quick scenario here of, let's say you have a snow cone and it's filled up with water, and of course as snow cones do, they start to drip and make a puddle. And so let's say your snow cone is dripping, and a little bit later your snow cone now is half full. There's a bigger puddle on the ground. And then a little bit later from there, your snow cone has very little liquid left in it, and you've got an even bigger puddle on the ground. So, what does this scenario give us for implicit differentiation? Well, there are lots of rates of change. First thing I look at is the volume. The volume is changing. Hopefully that's nice and obvious. As time goes on, the amount of liquid gets less and less. And because it's changing, there is a derivative involved. The derivative of volume with respect to time is changing. There is a rate there, okay? So that derivative would tell us how fast the volume is changing. Alright, so the volume is changing. Well, what else is changing? If we take a look at the amount of liquid left in our cone, the height of the liquid. The height of the liquid is also changing. As you can see here, it's getting smaller. So, height is changing. That means we have another derivative. There is a derivative of the height with respect to time, which will tell us how fast the height is changing. Alright, we've got that derivative. Let's see, is there anything else that's changing? Yes, there's one more. The radius of this bit of water. There's the radius, there's that radius, and here's the third radius. Each radius is getting smaller. R, R, R. Well, if the radius is changing, we have another derivative. I'm going to write that up here. The radius is changing. So therefore we have a d, oops, I won't write that there. We have a dr dt, which tells us how fast the radius is changing. Alright, and as you can see, all of these derivatives we're looking at are all related to the amount of time that has gone past. The change in the volume is related to the time that's gone past, the change in the height is related to the time that's gone past, and the same thing for the radius. Everything is based on time. They're all related by time, and so in a little bit we're going to be studying these related rates. But that's next time. That's where we're going. For now, we have to figure out how do we deal with having multiple derivatives. we've only usually been dealing with one derivative, dy dx, not two derivatives or three derivatives in this case. How do we deal with all that? And that is why we're going to be looking at implicit differentiation. That is going to allow us to deal with each derivative so we can do related rates a little bit later. So let's take a look at what this means. So first, the derivative in general. So we're not talking about related rates right now, just derivatives. If you have a function y equals 5x squared minus 6x plus 2. Right now we can all take the derivative nice and easy. Y prime equals 10x minus 6. And one thing that's going to be helpful here is for us to start thinking about that in a different notation. So we still have this equation y equals 5x squared minus 6x plus 2. It's going to be helpful to think about this taking the derivative of y with respect to x. Then you can say if you're doing it to one side of the equation, you obviously have to do it to the other side, like all things algebraic. Okay, and so you take the derivative that way, so that in the end you're left with dy over dx is equal to 10x minus 6. You can take the derivative of each one. And so of course you get to the same thing, but we're using this notation now instead of this notation, which they are the same thing, but in implicit differentiation I think this is the notation you're going to want to use. It's a little bit easier for many things. Alright, now that's what we've been doing. Why is that so easy? This is easy because we have an explicit function. And that simply means y is by itself. Nice and easy. But we're not going to look at explicit functions right now. We're going to take a look at explicit functions. Oops. Alright, an explicit function. Well, what is an explicit function? An explicit function is where y is not by itself. Alright, that's what we want to take a look at. What if y is not by itself? What if we have an equation kind of like this? If we have x squared minus 2y cubed plus 4y equals 2. Wait, I wrote that wrong, didn't I? I'm sorry. An explicit function, y is by itself. But we're not going to do an explicit function. We are going to do an implicit function, as our title said before. So on an implicit function, y is not by itself. Got a little ahead of myself there, I apologize for that. Alright, so an implicit function, y is not by itself. We have an example of an implicit function right here, and we want to take the derivative of it. We eventually want to get down to the derivative of y with respect to x equals. We want to know what is y prime. So, in order to do that, just like we did before, we're going to take the derivative of both sides. We're going to take the derivative of this side with respect to x, and we're going to take the derivative of this side with respect to x, just like we did up here. As you can see, it looks exactly the same. Although this one will be a little bit more complicated. To get us started, let's do the easy stuff. We can do this derivative. That is going to be 2x. We can do this derivative over here. The derivative of 2 is simply 0. However, these two are different. As you can see, we're taking the derivative of y. We haven't done that before. We have not taken the derivative of y quite. And so I'm going to single out this, I'm going to single out this term right here, and we're going to look at that one by itself. So over here on the side, we've got the derivative of negative 2y cubed with respect to x. Now, we can't do that because the variables don't match. So, what we're going to do is we're going to do something we can do. We're going to take that derivative with respect to y. That we can do, the variables match. We can use the power rule, so that will be a negative 6y eventually, y squared. But, of course, I can't just change a dx into a dy. That's illegal. They are obviously not equal at this time. So I have to multiply by something to make these equal. I have to do something. And what I do here is I do dy over dx. Algebraically, this works out quite nicely because, as you can see, the dy's would technically cancel out and the dx would slide over. But I'm not actually going to cancel those out because I want the dy on the bottom. So I can actually get down to negative 6y squared. But algebraically, that works out quite nice. So at the end, I have negative 6y squared. I have to add a dy dx. And that is the derivative of that single term. Now, if I lost you there, I'm going to try to pick you back up here. We're going to come back to our problem over here and take a look at this term one more time. So, in a nutshell, if I want to take the derivative of that when the variables do not match, I simply take the derivative like usual, negative 6y squared. But because the variables did not match, I have to add a dy dx. Alright? So the next one, I have the derivative of plus 4y right here. And so the derivative is just as usual, plus 4. But because the y and the x do not match, I have to add a dy over dx. So I've just taken the derivative implicitly, and now I'm going to do some simplifying. I want to get dy over dx by itself. That is my derivative. So I have to get these two terms by themselves. So do a little algebra here. Subtract 2x from both sides. The 2x's go away. I'm left with negative 6y squared dy dx. Those are multiplying. Plus 4 times dy dx equals negative 2x. Alright, let's keep going. I see that both terms have a dy dx, so we can factor that out. And when you factor that out, you're left with a negative 6y squared plus 4 equals negative 2x. And then if I want to get dy dx by itself, I simply divide both sides by this whole thing. Divide it by that whole thing. This goes away. and you are left with negative 2x over negative 6y squared plus 4. That is now our derivative of y with respect to x. It's fairly complicated. As you can see, we again have an implicit equation because we have an x and a y where y is not by itself. It shouldn't be too surprising if you start with an implicit function taking the derivative. You will usually end up with an implicit derivative as well. I hope that kind of takes care of the basics here. I hope that helps make your homework make sense.